Okay, so let's just jump right in. We are living in a world of multi-core processors. I mean, your phone, your laptop, even your watch probably has a bunch of them. And the promise has always been pretty simple, right? More cores equals more power. But it's just not that straightforward. There's this paradox, really, at the heart of modern computing, and it's the reason why just doubling the cores doesn't automatically double your speed. And that really brings us to the big question for this whole explainer. You go out, you buy a brand new computer, it's got an 8-core processor. You'd think it would be blazing fast, like 8 times faster than an old single-core machine. But a lot of the time, it isn't. So what's going on? What's the holdup? Well, the answer really starts with one of the most basic ideas in parallel computing. It's all about where your data is. See, every single processor core has memory that's physically right next to it. That's its local memory. Getting data from there? Blazing fast. But if a core needs data that's attached to a different core, it has to go get it. That's a remote memory request. And that is painfully, painfully slow. And here's the thing you've got to understand. When we say slower, we don't mean just a little bit slower. Our source material points out it can be hundreds or even thousands of times slower. This is not a small little hiccup in performance. It's the difference between shouting to someone in the next room versus trying to have a conversation with someone on another continent. It's a huge performance hit that programmers are always trying to avoid. Let's make this super concrete. Take a look at this ridiculously simple line of code. You'd see something like this everywhere in scientific computing or data analysis. All it's doing is adding 2 numbers from 2 lists. But here's the catch. If the data for X is on core 0 and the data for Y is on core 1, then for every single one of those additions, the processor has to make one of those painfully slow remote memory calls. Your performance doesn't just dip, it completely falls off a cliff. So, if the hardware itself gives us these massive challenges, how do developers even begin to deal with it? You can't just write code and cross your fingers. You need real strategies to manage this swarm of cores and make sure all the data gets where it needs to be. This is where you get into the real art of parallel programming. And developers have a few different weapons of choice. There's something called PGAS, that's Partition Global Address Space, where programmers basically act like traffic cops, telling the data exactly which core to live on. Then you've got GPUs, which we're about to get into, that have a totally different way of handling massive parallelism. And for the folks on the absolute cutting edge, there are hybrid models that makes everything together for the best possible performance, but they are incredibly complex. Now let's talk about GPUs for a second, because they are everywhere today, especially with AI and big science problems. Programming for a GPU is what we call heterogeneous programming. You're not just writing code for one computer anymore. You're basically conducting a dance between 2 totally different processors. You've got the main CPU, which we call the host, and the GPU, which we call the device. And the really critical thing is they have completely separate memory. So how does this dance actually work? It's basically a 4-step shuffle. First, the main CPU has to set aside memory for the problem on both itself and on the GPU. Step 2, it has to physically copy all the data it needs over the wire to the GPU's memory. 3, it kicks off the calculation on the GPU. And then finally, when all the heavy lifting is done, the CPU has to copy the results back. And you better believe every single one of those copy steps is a potential bottleneck. But it's not just about memory access. There's this other really common bottleneck that can bring a super powerful parallel program to a screeching halt. And it's something as simple as input and output, reading a file or just printing something to the screen. I mean, think about it for a second. What do you think happens when you have hundreds, maybe thousands of different processes all running at the same time, and they all try to write to your screen at the exact same millisecond, or they all try to read from the same file? You get chaos, just complete chaos. The output is a jumbled mess, data gets read wrong, and your whole program becomes totally unreliable. So to prevent that kind of chaos, programmers have to follow some pretty strict rules of the road. For example, it's a common convention that only one process, usually called process 0, is ever allowed to read keyboard input. And while, technically all the processes can write to the screen, it usually gets funneled through one process so the messages don't get mixed up. And the big one, any single file should only be touched by one process at a time. It's all about bringing order to that potential traffic jam. Okay, so we've written our amazing parallel program. We've wrangled the memory, we've sorted out the I/O. Now comes the moment of truth. Was it all worth it? Is the thing actually fast? We need some way to grade ourselves, like a report card for our parallel code. The first grade on that report card is a number we call speed up.
The math is super simple. You just take the time it took to run on one core, the serial time, and divide it by the time it took on all your parallel cores. The absolute dream, the holy grail, is something called linear speedup. That's where if you use, say, 8 cores, you get an 8-time speedup. That's perfection.
But speedup alone doesn't really tell you the whole story. For that, you need to look at efficiency. And again, the math is easy. Just take your speedup and divide by the number of processors you used. This number tells you how well you were actually using all that expensive hardware. An efficiency of 1, or 100%, means you hit that perfect linear speedup. Anything less than that means your processors were spending time on parallel overhead, things like communication or waiting on each other, stuff that just doesn't happen in a simple serial program. And this right here, this is what happens in the real world. This data is straight from our source text, and it's a classic example. Look what happens. As we add more processors, from 1 up to 16, our speedup keeps climbing. It goes from 1 to almost 11. That's great. But look at the efficiency. It drops from a perfect 1 all the way down to about 0.68. So we're getting faster, sure, but we're also getting less and less bang for our buck with each new processor we throw at the problem. And this gets right to the heart of the trade-off in parallel computing. The very act of adding more processors to solve a problem almost always adds more overhead. It just makes sense, right? More cores means more talking between them, more coordinating, more waiting. And all that overhead starts to eat away at your performance gains. It's the reason efficiency almost always goes down as you scale up. But here's where it gets really interesting. There's a twist. Check out this chart. We're using a fixed number of processors here, 16 of them. But look how the speedup totally changes based on the size of the problem. A small problem gets a pretty lousy speedup, but as the problem gets bigger and bigger, the speedup gets much, much better. So why is that? Well, with a bigger problem, the cores spend way more of their time doing actual useful work and proportionally less time on all that communication overhead. So all of this thinking, it leads us to one of the most fundamental rules in all of computing. It's a theoretical law that basically puts a hard cap on our parallel ambitions. It's called Amdahl's law, and you can think of it like a universal speed limit. And what the law says is actually pretty simple. It says that your total possible speed up will always be limited by the one part of your program that just cannot be run in parallel. Every single program has some little piece that has to run sequentially. Maybe it's loading the initial data, whatever. That tiny serial fraction acts like an anchor, weighing down the performance of the whole thing. Let's use the example from the source text. Imagine you are a programming genius, and you manage to parallelize 90% of your code, an incredible feat. Only a tiny 10% is left that has to run on a single core. That sounds like a massive win, doesn't it? So this is what that looks like visually. You've got this huge 90% chunk of your program that can be split up over 1 billion processors. It becomes practically instant. But you are still stuck with that stubborn little 10% slice, that inherently serial part. And it doesn't matter if you have 1,000 cores or 1,000,000 cores. That part of the code is going to take the exact same amount of time to run. And here is the punchline. For this program, even if you had an infinite number of processors, the absolute maximum speedup you could ever get is 10 times. That's it. That little 10% serial part creates a permanent bottleneck. You just can't get past the math, which is 1 divided by that serial fraction of 0.1. It's a hard physical limit. Now, that sounds kind of depressing, right? Like, why even bother? Well, hold on. The real world is a bit more nuanced. First off, like we saw a minute ago, that serial part often gets smaller and smaller as the problem size gets bigger. Also, scientists and engineers get absolutely world-changing speedups on real-world problems all the time. And at the end of the day, a 5x or 10x speedup on a simulation that used to take a month to run, that is still a massive, massive victory. Which really leaves us with this final thought to chew on. We definitely know how to build hardware with more and more and more cores. That number is just going to keep going up. But as we've seen, just having the cores isn't enough. So the real question for the future of computing might be this. Is the biggest challenge really building the next chip? Or is it learning how to completely rethink our software to actually use the incredible power we already have?